Diagonal line means multiplication by row. So now you understand the polynomial aspect of it. Here we have a class theta. This class here is theta over tau. Next class is theta over tau squared, etc. So I don't mean that tau is invertible. It's not. But this is just a convenient name to give that class because when I multiply by tau, I get theta. Okay? And likewise, this class is theta over rho squared, etc. Okay? So you have this infinitely divisible chunk of the ring. Okay? This is a non-Noetherian ring, although it's not a terrible non-Noetherian ring. When I come over here to the integral coefficients, it's very similar, and I just need you to get a general feeling for this. I don't need you to know the details. But so in this picture, box is z, and dot is z mod 2. So I again have sort of all these z2s, rho and rho squared and rho cubed. This time I have a class x up in dimension 0, 2, x squared, and so on. I still have my same class theta, or more precisely, this is an integral class. This is its mod 2 reduction over here. And then theta is infinitely divisible by x's, and then u, etc. Okay, so just keep in mind that things are a little bit more spread out in the integral picture. I have this jump of 2 instead of a jump of 1. And I have these integral classes mixed in with the z2 classes. Okay, so these are the cohomology of a point. And the cohomology of any space is a module over this. Okay, so one thing we'll be wanting to think about is what kind of modules we have over these rings. Every module over the polynomial ring is a module over this bigger guy, this M2. And so there's lots of things that can happen, as we'll see. One last thing I want to point out before I sort of scroll up and move to the next page. So all of this stuff and all of this stuff is in the image of the Hurevich. So all of that stuff comes from homotopy groups of spheres. And let me just explain that, at least a little piece of it real briefly. So S11 is this object. It's a circle with the reflection on it. And inside there, you see 2 fixed points, which is an S00. And this map is rho. Okay, so that's an interesting map on the homotopy groups of spheres. And when you compose with the Hurevich map going into sigma 1, 1 of H, then you get this rho here. For theta, you start out with S22, which is a sphere with the rotation action. So it's a 180-degree rotation about the central axis. So you quotient by modding out the C2 action. That gives you another copy of S2, but this time with trivial action. This map, maybe I'll call it theta tilde, because it's a map on the homotopy groups of spheres, but again, when I compose and go into H, it becomes this element theta. And the one thing I want to call your attention to, so there's a forgetful map from the HPQ groups into ordinary HP groups. This is classical singular cohomology where I forget all the equivariant stuff. When I take theta tilde, this map, right, this is a map from S2 to itself. When I just forget and think of it as an ordinary element in the homotopy groups of spheres, it's multiplication by 2. So what happens when I reverse the process? So things that you're used to seeing as multiplication by 2 sometimes show up in the equivariant world as multiplication by thetas, or even multiplication by, I scroll down, theta over x or theta over x squareds, etc. Okay? You should think of these theta classes as some equivariant forms of multiplication by 2. Okay. So keeping all that in mind, you now know the cohomology of a PQ sphere. Let's just be Z2 coefficients for a while. So this is just the cohomology of a point shifted up. So I'll denote it this way. So you take the M2 thing that I just showed you and shift it. And there's one other kind of sphere that I'm going to need to use in this talk. So I can take Sn with the antipodal action. Okay, that's not a representation sphere. It's not one of these SPQs. When you compute the cohomology of this, well, let me draw the picture here. So you get a bunch of vertical lines. Remember, vertical lines is multiplication by tau. And then you get a bunch of diagonal lines. And diagonal lines are multiplication by that class row. Okay, and that's what it is. Okay, so this is depicting an M2 module. And so it starts in dimension 0 and goes up into dimension n. It's a bunch of Z mod 2s connected by these multiplication by taus and multiplication by rows. Okay. I'll call this AN, although it won't come up a whole lot, and I'll probably have to remind you what AN is when it comes up again. Okay, so far what have we seen? So we've seen M2 and we've seen these ANs. There's lots of other M2 modules. So let me show you a computation where these come up. So I'm going to take a look at a Grassmannian, GR2 of R42. So you can do the usual Schubert cell decomposition of a Grassmannian, and you get an equivariant cell decomposition. You actually have some choices, so that the Schubert cell decomposition depends on a choice of flag, which is really the same as a choice of ordering your basis in some sense. In a representation, you have different kind of basis elements. So on some basis elements, the action is trivial. On some basis elements, there's an action of a sign. And so different ways of ordering those basis elements give you different Schubert cell decompositions. But one of them looks like this. So you have a 0,0 cell, and a 1,1 cell, and a 2,1 cell, and another 2,1 cell, and a 3,1 cell, and a 4,4 cell. I'm not going to go through the calculation of how I got those numbers, but it's not difficult. So this cell filtration gives you a spectral sequence for computing the cohomology, and I want to now go through that spectral sequence with you. It's not too difficult. So I'm going to pull up another file here. This one was called something like cell spectral sequence. There it is. Let me move that over a bit. Okay. All right, so I'm going to talk you through this. So here's the E1 page of our spectral sequence. Can I scroll this back down a second? No, I think I covered up my cell diagram. So this X, let me write it up one more time. So there was a 0,0 cell, a 1,1 cell, a 2,1, a 2,1, a 3,1, and a 4,4. Okay, so each of these cells you see giving me a copy of M2 in this picture, except I've drawn the reduced cohomology, so I'm not going to draw that guy. Here's my 1,1 cell. Over here in the magenta color are my 2,1 cells. My 3,1 is in blue, and my 4,4 is way up here in orange. Each cell gives me a copy of M2, forming this picture. This is really a trigraded spectral sequence, so it's bigraded because of the cohomology, and then there's the filtration dimension. The filtration dimension is suppressed in these pictures, so you really see it in terms of the colors. The differentials in these pictures, they all go exactly one to the right. Okay? The differentials change the filtration dimension, but you're not seeing that because it's suppressed. So this is a D1, but it's also a D2 and a D3. All the differentials do the same thing in terms of the grading. Okay, so when I look at this, I see I have to understand what happens on the generators. Okay, all the differentials preserve the M2 module structure. And okay, there's a bunch of possibilities for what happens on all these generators. But classically, you know that all the differentials are 0, right? And in singular cohomology with mod 2 coefficients, all the differentials are 0 for these Grassmannians. So instead, you can't have a differential like that from generator to generator, because then when you forgot into the non-equivariant singular cohomology, you would see the same differential. So most of these differentials are immediately ruled out. The one that isn't, what would be a good color to use here, is this one. Okay, so when I go to singular cohomology, all this stuff in the negative cones just disappears, and I don't see it. And so there's a possibility for a differential there. We do not have a good way of predicting these differentials. We have 0 geometric understanding of them. Okay? So Eric Hogel came up with an argument that this differential actually does exist. Okay, so I'm just going to put a check mark here. I'm not going to go through the whole argument with you. Just take my word for it, because I want you to see how the computation plays out. But that differential does exist, which means that this class up here, which is tau times my generator, hits tau times this generator. Everything else sort of goes to 0, and I'm left down here. Here's my E2 term. So the blue cone has been replaced by this blue sort of W shape. There was a generator here and here that disappeared. Okay, so you can sort of see the remnants of a cone. And likewise, the inverted orange cone got cut off and gave me an inverted W shape, which is here. Okay, so now we need to think about more differentials. And the only place anything could happen is down here in this dimension. Okay, where I could have differentials from my pink generators here and here that could possibly hit that guy. Up to a change of basis, what happens is that one of them hits and one of them is 0. So I'm going to put a check mark just to say that that differential actually does appear. So that ends up truncating the orange W shape, and it ends up truncating the pink inverted cone, and we go over here to E3, and you get this shape. Okay, so there's the remnant of the pink cone, and we still had that remnant of the W cone, and here's the leftover remnant of the orange stuff. Okay.
Dan, can I ask a question?
Yes, please.
So I would think that the D1s, there's that suppressed filtration, and I would think the D1s would like increase like the dimension by 1 or something. So that's why you go from blue to orange, because it's like 3 to 4.
Right.
And then I would expect the D2s to increase dimension by 2.
Yes, exactly.
So that goes from, but the pinks, but that looks like it's just 2 to 3 still.
No, so what's happening is that the dimension is the color. Okay, so purple is dimension 1.
Right.
Pink is dimension 2. Blue is dimension 3. Orange is dimension 4.
Oh, I see. It's from pink to orange. Yes, from 2 to 4.
Exactly. It's from filtration 2 to filtration 4.
I misread the picture. Okay, thanks.
Yep. Great. Okay. Right. So here's the E3 term, which is this crazy looking thing. Everything here that we're drawing are M2 modules. Okay, so every picture you see here is a picture of an M2 module. This is E infinity. There's no room for any more differentials. But you do have extension problems. And the way those extension problems all get worked out is that everything ends up free at the end. And so here's your final answer. So even though you went through this stage, intermediate stage of all these crazy M2 modules, at the end, everything's free. And here are your generators. And what I want to call your attention to is, so, and these are the usual Schubert cell generators. If I just look in each topological dimension, which are the vertical lines, okay? So I had one generator here in dimension 1. I had 2 generators here in dimension 2, 1 generator in dimension 3, 1 generator in dimension 4. That's my usual singular cohomology of a Grassmannian with mod 2 coefficients. The new data is what the weights are, okay, where they end up in this bigraded picture. All right. Any questions about this computation before I move on? Okay, sounds like everybody's good.
No, I had a question. I was trying to raise my hand.
Yeah.
Is there a comparison with a motivic computation for to take Grassmannian over R, which is the right weights of
Right. So
over R Grassmannian 2, 4.
Yes and no. So what's the right answer to this? Let me see if I can scroll down a minute. So when you do algebraic Grassmannians, it's much more like this. Okay, so this is the right analog to those naive algebraic Grassmannians. You can write down an algebraic scheme, which is a Grassmannian of, okay, what did I used to call it? So it's the quadratic Grassmannian. So you put yourself a split quadratic form under your underlying space, and you look at the Grassmannian of subspaces where the form restricts to be non-degenerate. Okay, so there is such a thing called a quadratic Grassmannian in algebraic geometry. And these things that I'm doing right now, so that's the motivic analog of what I'm doing right now. I guess that's the answer to your question. But the problem is, go ahead, Kristen.
Well, okay, never mind. Sorry, I take it back. Yeah.
Okay. But the thing to add, though, is that most of these cell filtrations that you see in the Z2 equivariant world, they are not motivic. They are not analogs of algebraic cell decompositions that you have for these quadratic Grassmannians. And one reason you kind of know that is that the heavy interaction of these negative cones. So these negative cones do not appear in the motivic world. And so somehow what you're seeing in this whole spectral sequence doesn't seem to have a direct motivic analog. Anyway, that's about all I know about that problem.
Thanks a lot.
Okay, any other questions? Okay, let me just scroll up here. Yeah, if you try to raise your hand, it's hopeless because it's not on my screen. So just scream out. Okay, so right, so we saw this complicated thing where things sort of got complicated and crazy, but then they reassembled and they were all free at the end. So this always happens, and it's the theorem of Bill-Cronholm's. Which says that if X has a decomposition in terms of SPQ cells, then the cohomology of X, this is with Z2 coefficients now, is always a free M2 module. Okay. And his proof of this was highly computational and hard to get any ideas out of. It was sort of an elaborate investigation of what's happening in these spectral sequences and what the extension problems can look like, and sort of a long case analysis that we didn't understand. I'm going to come back to this later because I think we now have a better understanding of this theorem and why it's working. But let me point out that you definitely need some hypotheses here. So if you think back on those SN antipodals, right? The cohomology was not free as an M2 module there. And that's because you don't have these special kinds of cell decompositions. Okay. So this is all taking a lot longer than I thought, not surprisingly. It's the way these talks always go. So here's the question. So find the cohomology of these equivariant Grassmannians. So what you know about it is that it's free over M2. Okay. And the generators, so it's the usual number of free generators in each topological degree. And the only uncertainty is what are the weights. So it doesn't seem like this should be a hard question, but it's unknown, and we've been struggling with this for years. Let me just tell you a little bit about what's known about it. So there was a theorem of mine from a few years ago where I was able to do the infinite Grassmannian. So if you take GRK for the complete universe, so infinitely many copies of R with the trivial action and infinitely many copies with the sign action. Here, let me just say this. So this one's known, and the number of free generators in bi-degree PQ is the number of partitions of P into less than or equal to K pieces. Okay, that would be the usual answer for the Grassmannian, in singular cohomology. But I need to add a condition here where exactly 2Q minus P pieces are odd. Okay? So it's some weird combinatorial condition about what the partitions look like. So you write down all your partitions, you see how many odd pieces you have, you stratify those, and that predicts where they are in this bi-graded picture. One thing I want to say about this theorem, its proof was really strange and kind of sneaky. If you write down the cellular spectral sequence, there are infinitely many differentials. And I have no idea what those differentials are. I have no idea how that spectral sequence works. But by various sort of sneaky things, I could end up using Cronholm's theorem to predict what happens at the very end. But that's an interesting question. What are the differentials in that spectral sequence? And understanding these differentials is somehow the obstruction we have to understanding, solving this problem in other cases. Okay, so I just wanted to briefly mention what Eric Kogel has done with this. So he's completely solved two cases. So if you take the Grassmannians on R n comma 1, so with one sign representation, so he knows the answer here. And in bi-degree PQ, it's, let me see if I can write it. It's partitions of P into less than or equal to K pieces. Okay, this is a finite Grassmannian, so I need a constraint on how big those pieces can be. And the usual constraint is n minus K. So you're not surprised so far. But here, these partitions have to have trace Q. And so what's the trace? The trace is something that would already be considered by combinatorialists who study these Young diagrams. I'll just draw a picture here. So if this is a Young diagram, then the trace is how many guys you can cross with your main diagonal. Okay, so this is trace equals 2. Okay, so you write down all your Young diagrams for your partitions, you sort them according to the trace, and that gives you the bi-graded picture for these GRK Rn1s.
Hey Dan, is the Rn comma 0 case, is that like trivial?
Yeah, so the Rn comma 0 case, you just get the generators stacked up along your horizontal line, nothing happens, and so that's your answer. So everything's in weight 0 there. The other case he's done is the GR2 for Rn2s. And I'm not going to tell you the answer because it's sort of complicated, and for us so far, it's not very enlightening, but we have an answer here, or Eric has an answer. And here we don't have some nice combinatorial description. But this is sort of an interesting question, right? I mean, we're taking young tableau of a certain type, and then we're sorting them according to this topological weight. You would expect that to have some kind of combinatorial description. So that's an interesting open problem. Okay. I can't scroll for some reason. There we go. I feel a little bit like I'm shortchanging Eric's work just by sort of highlighting these two pieces. What he's done is he somehow found a way to understand these cellular spectral sequences a little better than we have before in the case of Grassmannians. But these were sort of the two concrete cases that his techniques allowed him to answer. Okay, so I'm going to leave Grassmannians for a while, and I'm next going to talk about surfaces. Change the page of my notes here. So first of all, what are all the Z2 surfaces? And by surface, I mean, compact, closed, no boundary, just the usual thing, except those kind of surfaces. So we understand surfaces completely, non-equivariantly. You wouldn't think that adding the Z2 action is much more difficult. And to some extent it's not, and to some extent it is. So on the genus G torus, it's very easy. You have 4 plus 2G of them. And you can write them all down. I'm not going to do it at exactly this moment. But you take a little time and think about the obvious Z2 actions on tori, and you'll write them all down. Okay. And this has been understood at least since the time of Felix Klein, back in the late 1800s. In the non-equivariant case, well, this has been worked on over the years, and you can trace it back at least to the 1920s where people were thinking about it and knew a lot of them. And then it sort of recurred again in the 1970s. There's a bunch of papers where you can find partial information, but I was not able to find a complete answer. But I worked one out about a year ago, and it's much more complicated than you would think. So I'm not going to write down all the formulas because they're complicated. But I will say that asymptotically, the number of actions you have is r cubed over 64. So again, not linear in this case. And again, I have sort of complete formulas for exactly how many actions and how to write them down. But I'm not going to go through that today. My point is just that there's a bunch of them. Okay, so I asked second student, Christy Hazel, to work out the cohomology of all these surfaces, and I want to show you her computations. I'm not going to go into these in detail, but I want you to just look at the pictures and absorb something from them. So I'm going to change here into different software, if I can find it. Okay. So let's see. All right, so here are certain free actions on tori. On the left, you have the integral calculations, and on the right, you have the mod 2 calculations. I'm just going to kind of scroll through these, but what I want to call your attention to, I guess, different things as we go along. So in blue, you have something that looks like the cohomology of S2 with the antipodal action. In red, you have this one line, which is the cohomology of an antipodal zero sphere, or if you like, just Z2 itself. And you have a bunch of copies of those. You have 2G copies of that red line. Down here, this is another action, another free action on a torus. You have these two blue bars, which look like two copies of S1 with the antipodal action. Okay, moved around a little bit. And then you have that red bar in the center. Here are more calculations. Here are more calculations. By the way, Christy, she was very annoying because I gave her this project and I hoped it would keep her busy for like 6 months. And then she came back about a week later with this whole document. And then I had to find something else for her to do. But so here's an example where you have a couple M2s and you have those red bars. The integral calculations are, of course, much more intricate. But I want to point out that over and over again on the Z2 picture, you're not seeing much. You're seeing M2s, you're seeing bars, you're seeing those S1 or S2 antipodals. Scrolling through to, okay, this is the first non-orientable guy. And let me say first, just to give you an idea, let me show you what's going on here. So first of all, what does this notation mean? So we're taking S2 antipodal, and I'm going to do something to it. The DCC stands for dual crosscaps. So what you do is you cut a hole and you identify opposite sides. Okay, that's like sewing in a little Mobius band. You do it here, and you do it on the antipodal side as well. Whoops, I just lost something. Let me find that page again. There we go. Okay, so I add a bunch of crosscaps and I add dual crosscaps here, so now I have an equivariant action. And I do that a lot. Here's an S11 circle. Okay, so that's the circle with our reflection action. Sorry, that's a terrible picture. Let's try to do better. So there's an S11 circle. I can form a tube. And I'm going to give this the action where this point is conjugate to this point. So we're sort of like a reflection, but the back side is reflecting over to the front side. Okay, so this is called an S11 antitube. Okay, the anti is just that telling us that that circle is conjugate to this circle. So I can cut out disk there and a disk there, and sew in one of these S11 antitubes. Okay, and I can do that a bunch of times. Sorry, this is a really awful picture. But that's what this means. Okay, so take an antipodal sphere, add a bunch of crosscaps, add a bunch of antitubes, you get a certain equivariant space. Okay, here's its cohomology. The number of vertical lines is one more than the number of crosscaps you added. The number of copies of M2 over in dimension 1, 1 is over here. Don't worry about the numbers. It's related to the number of tubes that we added. Okay, and then we have this one fundamental class up here in dimension 2, 2. Okay. I have no idea what any of this means. I just know that this is the answer. Okay. One of our goals is to be able to take this picture and actually figure out how do you get the cohomology from the picture, okay, in terms of geometry. The other thing that's cool about this example, and you can barely see it, but I want to call your attention to it. So the boxes are z's. So I'm going over to z coefficients here. And you're used to seeing this kind of pattern from the cohomology of a point. But what actually happens here is that you get a z4 that shows up there. That's what that circle is before dying into a z2. So for some strange reason, those z4s show up a bunch in the cohomology of these non-equivariant surfaces. Sorry, I didn't mean to say non-equivariant, non-orientable equivariant surfaces. You see the z4s coming up a lot. And again, we would like to be able to find some geometric reason for that z4, and we don't have that yet.
Dan, what do the dashed lines mean?
So there's in equivariant cohomology, there's this x. And I think what it means is that, so the x doesn't take that generator to that generator, but there's an extra multiplication by 2. Christy, I think you're out there. Is that what that means here? Okay, thank you. Okay, any other questions about these pictures? Again, I'm not expecting anybody to absorb much about these calculations other than the general flavor of what the answers you're getting look like. Okay, so let me scroll down one more time and just point out, oh, my scroll is screwed up somehow. I think I did something. Never mind. So before Christy sort of completed this project, Clover and Eric had already done these calculations in genus 1. And what was already apparent there is what I've mentioned already, which is that over on the Z2 side, you're only getting copies of M2 together with these vertical lines, and then those things that look like the cohomology of antipodal spheres. All of the exotic M2 modules that were showing up in our spectral sequence calculation earlier today, those were not appearing in any of the final answers. And I think we now have an explanation of that. So let me bring my whiteboard back. And this will be, whoops, that's not a whiteboard. There's my whiteboard. Okay, and this will be the last topic for the day. So let's find another color. Okay, so here's the theorem from Clover May's thesis. So X is any finite CW complex with an equivariant structure. Okay. And I want to contrast this with Cronholm's theorem. So remember, Cronholm's theorem assumed that we could build our space from the SPQs. Okay. This is much more general. Okay. This is essentially any equivariant space, although there's a finiteness condition right now. So she proved that the cohomology of X with Z2 coefficients always splits up. So you have suspensions of M2s, and then you have various suspensions of those AN guys. Okay. And remember, AN is just this picture. It's the cohomology of an antipodal sphere. Okay. So those are the only things that ever appear. And the reason ends up being pretty interesting. So let me tell you the story, because it's kind of a neat story. So what happened was that Eric Hogel and Clover May were learning about Cronholm's theorem. They were reading his proof, and they found a gap. There was a very subtle gap in the argument that all the rest of us had missed. And so they found this gap and gradually convinced me that it was a problem. And then they worked on fixing this, and they had a very elaborate argument chasing through the spectral sequences that eventually did fix this problem. And then last winter, I was visiting Wayne State and talking to Dan Isaacson about this. And he sort of immediately honed in on a Massey product explanation for this, or at least the suggestion that such a Massey product should be the reason why this was happening. So then I came back and asked Clover to think about this Massey product. And indeed, that's what led to this theory. So if you remember back for the cohomology of a point, we had these special classes tau and rho, and then also this special class theta. Let me see if I can scroll up here. And so Clover proved that there's a Massey product decomposition of 1. So 1 is the Massey product of tau, theta, and rho. So this is a weird thing, and I don't know any other place in topology where you get an interesting Massey product decomposition of the 1, the unit in your adjunct. But using this, and using that the cohomology of any space also has Massey products, and that they're compatible with the Massey products in the cohomology of a point, she was able to show that this directly implies the above theorem. Okay. So all the crazy M2 modules that you can write down, none of them are compatible with this Massey product decomposition. So that was very nice. And as a consequence, Hogel and May have given a new proof of Cronholm's theorem. And I told you before that the original proof of this was chasing through the cellular spectral sequences and thinking about the possible extension problems, and it was sort of a long analysis. But I think that they're able to get this directly from this kind of decomposition. So all they need to check is that if you have a space which is built from SPQs, then you can never get these ANs appearing. Once you realize that, they're gone from the picture and you just have your M2s left. So that's the idea there. Okay, let me say one more thing. I think I'm actually almost done, a little bit early. So 2 questions of sort of things that come out of all this stuff. So one is you could think about the category of HZ2 modules. Okay, so this is the Eilenberg-MacLean spectrum corresponding to our equivariant cohomology theory. There's a model category of HZ2 modules, and you can sort of play around with it. And you could ask, is there a nice description of this? So what do I mean by a nice description? Well, one possible way to go is sort of write down generators, basic generators, and the maps between them. The Clover-May's theorem that I mentioned before, I have to always remind myself to say Clover-May, because if I just say May, you're going to think of a different May. But so this theorem is somehow the beginning stage of a piece of something, right? It's probably saying that any HZ2 module splits as free HZ2 modules and these kind of HZ2 modules. This is the pi star version of such a theorem. And so you would expect that maybe this gives you, saying, you know, some kind of nice description of this category. The other thing I've been curious about for a long time is whether there's a DG model of this. Okay. So can you write down an algebraic model category? So one equipped with an enrichment over chain complexes that models this category. I don't think anybody knows how to do this, and I've received sort of conflicting opinions from experts about whether this is possible or not. But certainly you should be able to either answer, is it possible? And if so, do it. What does it look like? So I'm very curious about that. The second thing I want to mention, this is maybe, well, this is a question, I guess, but this weird ring M2. So this comes up in a completely different way in another area of mathematics. So if I'm in algebraic geometry, I can look at the cohomology of P1 with twisted coefficients. And just for, it doesn't matter what field I do, but just for the best analogy, let's work over F2. So this is a bigraded ring that algebraic geometers call the Cox ring of P1. And it is exactly this ring M2. Well, I need to actually qualify that a little bit. So it's the same ring, but with a different grading. So what happens in the algebraic geometry world is you have 2 gradings, 0 and 1, because that's all the cohomology you're ever going to get out of P1. And what you see is you see that polynomial algebra with the tiles and rows all compressed into degree 0. And you see all the theta stuff compressed into degree 1. So it's M2, but with a different grading than we've been using. But what you can do is you can go check that you have that same massey product here. And this is crazy. Like, this has got to be way more than a coincidence. I don't know what's going on here. It's a natural guess to think that maybe actually this ring is best thought of as tri-graded, where you have sort of the topologist grading that we're used to, plus this extra grading coming from algebraic geometry. The way these spectral sequences often work out, the cellular spectral sequences that I was talking about before, that the interactions between the two pieces seem to be so rigidly controlled that it's not out of the question that somehow there's a secret grading that separated them that we couldn't see before. So the question here is, what's going on? And I think I'm going to stop there. Thank you.
Okay, I'm going to unmute everybody so that we can thank the speaker. Okay, and if there are some questions. Yes. Oh.
Cohomology of Grassmannians has interesting enumerative interpretations. So I was wondering if there's counts of equivariant lines that can be interpreted with results on cohomology of equivariant Grassmannians.
Yeah, that's a great question. And then when I saw your talk last, I guess it was over the summer, that same thought went through my head. We haven't explored that at all, but there's got to be some kind of nice answer to that. But I don't know it. It's a great question, though.
Also, do people look at, in algebraic geometry, do people look at modules over the Cox ring? And if so, does this Massey product limit the kinds of modules that would appear in algebraic geometry that would naturally be over the Cox ring?
Right. So what's the answer to that? So the geometers who I've talked to, they seem to use the Cox ring only in very, very limited ways. They do look at modules over it, and the first reason I became aware of this is I was sitting in a class on algebraic geometry, and I found them writing pictures